Is this thing on? Is this thing on? Captain's log, day 723 of quarantine. I ate a yellow Lego brick the other day. It looked like a Twinkie. I just don't know what to do anymore. I'm running out of math to go through. No, that's not real. There's always more math to do. There's always more math to do. Let's fix that photo booth. Anyways, let's get back into our ellipses. Got a few things to work through. Going to talk about properties of ellipses and throw a whole lot of stuff at you today. So I'm going to get over to my notes, take some notes, follow along. Let's see where we go. So what we have with an ellipse, as we've seen the past couple days, an ellipse is a set of all points such that the sum of the distances from each focus is constant. I'm going to switch back over to Desmos. Take a look at that. Not that one. I want that one. So here we've got an ellipse. What I've got going on in this setup is I've got an A value that can change. Down over here on the left side, the standard equation of ellipse, the A gets us that horizontal stretch or compression. The B gets us that vertical. Now you see those two purple dots in there. Those are our two focus points, our foci, F-O-C-I, if you will. Now, as we stretch, compress horizontally and vertically, those points move around. Now what we also see when it's set up right is that orange segment and the second orange segment, those are the sum of the distances, or those are the distances from a point on the ellipse moving around. Now if you look, I can toggle my C value here. Now this is a different C value, just a point set up so that it can travel around the ellipse. You see that over here the left orange segment is shorter than the right orange segment. But underneath, over here on the right side, left side, the sum of those distances is constant. In this case, based upon my A and B value, it stays 5.8. We change that based on the A and the B value, it switches around. But as we move our point somewhere around the ellipse, that sum is constant. That's what it means to be an ellipse. I'll leave that. Oh, that's not one that I want. So back to our standard equation of an ellipse. Reading through, we have different characteristics. Our center point, same as a circle, is that point HK. Now A and B give us the distances from the horizontal, from the center to the horizontal and vertical vertices. The A, the square root of the denominator of the x, gets us the distance to the horizontal values. The B, the square root of the y term, the denominator of the y term, gets us the vertical distances. Now those purple points, those foci, that's a distance of C away from the center. And so we get the C, it's C squared equals the absolute value of A squared minus B squared. I put in absolute value so that it is always positive. It's got to be a distance. Grouping everything together here, different characteristics that we look at: the major axis, the minor axis, the major axis vertices, the minor axis vertices, and our foci. Putting everything together, we can see that there's these similarities. What we need to do at the start is we determine, is our ellipse horizontal, is our ellipse vertical? Now these are not everything to remember, memorize, but just get the idea of that A gets us a horizontal distance, that B gets us a vertical distance, and together they get us the C to the foci. And so whether or not we're horizontal or vertical defines whether or not we have a major axis that's horizontal or the major axis is vertical. I'm going to go through an example and try this out, identify all the points there. So I've got x minus 3 squared over 4 plus y plus 1 squared over 25. Reading through this, our center we get from the shifts, x minus 3, y plus 1. We're going to have a center of positive 3, negative 1. It's really what value for x makes the inside equal to 0. What value for y makes the inside equal to 0. This case, our ellipse is going to be vertical because the denominator, the vertical stretch, is greater than the horizontal stretch. 25 is greater than 4. So our major axis is going to be vertical. Our minor axis is going to be horizontal. Our foci are going to be oriented vertically. Now we can find our major axis vertices. I take the center and I add the square root of 25 and subtract the square root of 25. So 1 to the y value, so -1 plus or minus 5. Our minor axis vertices are going to move left and right relative to the center. So I take the square root of 4, getting 2, 3 plus or minus 2. And last, we have our foci. We find that distance. Now 4 minus 25 is 21, -21, but absolute value. We can find the distance is the square root of 21. And since our foci are going to be vertical because we have a vertical ellipse, I can do 3, that's the center, 3 -1 is our center, plus or minus root 21. Putting this into the calculator, we'll take a look at it. Oh, that's the other page that I wanted. Let's see, can I get that back? Nope, I just deleted everything that I wanted. Oops, oh well. You can plop that in, take a look at it. Here we go. So I've got x minus 3. It looked blank, and I know my tricks that I was trying to do, and I messed that up. Plus 1. So we're going to have a center, 3, -1. We've got the vertical vertices. We've got the horizontal vertices. I'll put those in real fast. Those are our vertical vertices. We're going to have our horizontal vertices. And then we have our foci. Oops. So, switching some things around, just so we have some consistency. The two purple dots, top and bottom, those are our major axis vertices. The two red points are our minor axis vertices. Blue in the center is clearly the center, and the other two blue points are the two foci. And so we've got an example of a vertical ellipse. Other ellipse generator that I have here is just a way of seeing everything all together. So up top left, I've got the standard equation of our ellipse. I've got a bunch of sliders set up here so we can see, okay, if we move our ellipse, the center of the ellipse, left, right, wherever it's going, well, that changes the HK value. I can change the H, see that I've got a horizontal shift, change the K, see that I've got a vertical shift. Got an extra rogue point in there. What's that? Get rid of those bits. Now the A and the B value stretches the horizontal, and you see that it switches as soon as those foci start to go right towards the center. If they're right on the center, notice that A and B are the same in that case. Well, if A and B are the same, that's just a circle. If A squared is less than B squared, we have a vertical ellipse, and we can see that it's very much stretched out. Or if A is greater than B, we've got a horizontal ellipse. So there we've got all of our different characteristics, pulling it out. The next thing, just like with circles, we had different types of equations. Here we've got the standard equation of an ellipse, where we've got the center and we've got the horizontal vertical dilations. Now, we also have a general equation of an ellipse. That's not what I wanted. That's the paper that I wanted. So the general equation of an ellipse is if we multiply everything together. We take our standard equation, distribute the square, and multiply, rearrange things, we can turn that into the general equation of an ellipse. Notice that the A, the B, the C, D are not the same as these A's and B's. I just use ax squared plus bxy plus cx plus dy as just standard coefficients. These letters, coefficients, do not match these variables here. Now, if we are in the general equation of an ellipse, just like with the circle, it's not easy to find the center, find the radius. So we need to take that general equation of an ellipse, rewrite it in standard form by completing the square. So we're going to do this. We're going to first rewrite everything, group the x terms, group the y terms, take the constant to the other side. Completing the square, we need to add something so the x's are a perfect square factor. We need to add something so that the y terms are a perfect square factor. Now, what's different from the circle is that I've got a coefficient in front of the x. If nothing's written there, it is 1. So now I've got this 9x squared, this 16y. I'm going to factor the 9 out of the x terms. I'm going to factor the 16 out of the y terms. Now, this blank that we need to complete is not the same as this one because this 9 is being multiplied to whatever we're adding inside the parentheses, or this 16 is multiplying towards whatever we're adding inside the parentheses. We've got x squared plus 2x, complete the square. We realize we're going to add 1 to both the x term and the y term. Now, over on the right side, this 1 that we added is actually 9 times 1. So we've added 9 over here on the right. This plus 1 that we've added by completing the square for the y terms is not actually 1, it's 16 multiplied by 1, giving us 16 there. It's a perfect square. We will then factor. One more step. Going back, our standard equation of an ellipse, it's divided by that a squared divided by b squared equals 1. So I'm going to divide everything by 144. I'm going to divide by 144. That's going to leave us with 9x plus 1 squared divided by 144. But 9 over 144, or 16 over 144, reduces down. So we've got x plus 1 squared over 16 plus y minus 1 squared over 9 equals 1. We have our center. We have our horizontal stretch. We have our vertical stretch. I'm going to go back over to Desmos, take a look. The initial example that we had, compare it to the final outcome that we had. So here, we've got our 9x squared plus 16y squared plus 18x minus 32y minus 119. That was our initial. We've got our ellipse there. We can see our center is negative 1, 1. We have a horizontal dilation of 1, 2, 3, 4 in either direction, and we are 1, 2, 3 vertically from the center. Take a look. We've got x plus 1 over 16. We are a horizontal stretch of 4 in either direction from the center. We've got a vertical stretch of 3 in either direction. So there we've got an ellipse. Today we're going to work through mixing up the forms, graphing, and seeing how this is really just a special, circles are a special case of an ellipse. And I'm going to give you some other pieces. You've got to find the different parts, writing the equations. Good luck.